Good afternoon, and thank you for participating in this webinar. My name is Judy Kolva, your NTI representative. The National Transit Institute develops, promotes, and delivers training and education programs for the public transit industry in the United States. We are pleased to have Kathryn Coffel and Jamie Parks as our presenters. Kathryn Coffel is a leader in applying private sector research techniques to the field of transit. She provides consulting services from the initial strategic phases through design and implementation. She brings a bachelor's degree in business, a master's in planning, and over 25 years of transit experience working for a transit agency and as a transit consultant. Kathryn's work includes market and customer research, performance reporting, and fair policy analysis in support of transit planning. Kathryn is chairman for the Transportation Research Board's Public Transportation Marketing and Fair Policy Committee. Jamie Parks has worked on a wide variety of projects in transit planning, transit performance measurement, statistical analysis, and transportation research. Jamie also participated in several guidelines development and transit research projects, including serving as the Associate Investigator for TCRP Report 153, as a lead researcher for TCRP Report 141, and ongoing work on TCRP A15C. Jamie's applied planning experience includes work with Sound Transit to evaluate the potential effectiveness of a wide range of station access improvements, work with WMATA to develop a non-motorized station area access studies, and transit performance evaluations for transit agencies throughout the country. Now I will turn the presentation over to Kathryn.
Thank you very much. Jamie Parks will be leading this webinar, the second webinar of this series. I will turn it over to Jamie, and he can then introduce the topic.
All right. Thanks, Kathryn and Judy. So again, I'm Jamie Parks, and I served as the Associate Investigator for TCRP Report 153, and want to start off with a couple of acknowledgements for the rest of the team. Of course, Kathryn, who's here with us today, was the Principal Investigator on the project. Then, in addition, Connor Semler at Kittleson Associates, Herb Levinson, Dave Sampson at AECOM, Joe Schofer from Northwestern University, and Carol Ketchadorian from Tool Design Group all provided valuable input into various components of the research. And then, of course, want to thank as well our project panel and TRV contract manager, Diane Schweiger, for their support and oversight and guidance throughout the entire project. So I want to turn quickly to an overview of the research products that came out of the TCRP Report 153 work. So first, of course, is the report itself, which was published as the guidebook. And so the guidebook is split into two separate parts. Part one is focused on station access planning. So it includes an 8-step idealized planning process, insights from the case studies that we conducted as part of the project, and travel demand characteristics and data, including the spreadsheet tool that we'll focus on a lot today. Part two of the guidebook focuses on station access arrangement and design, and it's organized around specific access modes, so pedestrian, bicycle, transit, and auto. Second research product are the detailed case studies that we conducted as part of the project. So these were 11 detailed case studies of agencies around the country and one in Canada to highlight successful practices with station access planning, and really served as the key data or information source for a lot of information in the guidebook. The total case studies were about 150 pages, so they were not published as part of the guidebook itself, but as an online appendix and also as part of the CD that accompanies the print version of the guide. And then finally, the third primary research product is the spreadsheet-based station access planning tool, which we'll talk a lot about today. So webinar outline. Part one of the webinar, which was just concluded about a half hour ago, talked about part one of the guidebook. Part one of the webinar talked about the planning portion of the guidebook and insights from the case studies, as well as part two of the guidebook. The second part of the webinar, which we're starting right now, is focusing specifically on the station typology and data that we collected, chapters 4 and 5 of the guidebook itself, and then the spreadsheet-based access planning tools that we developed using that data, which are appendices C and D out of the guidebook. Now, what's not covered in the webinar at all are the stakeholder interviews that we conducted as part of the project. Those were Appendix A. And then the literature review, which was a comprehensive literature review conducted at the outset of the project, and that was published as TCRP Web-Only Document 44. And then we're also not covering Appendix B, which is an overview of existing station access tools. So with that, to briefly introduce sort of the scope of the project and what it was that we were trying to achieve with our research. I want to go over briefly what the scope of our research project was and then what the problem was that we were trying to address as part of the project. So first, high-capacity transit. We defined it as part of our research, as part of the project, as basically anything that's running in its own dedicated right-of-way. So pretty much anything that's rail, commuter rail, heavy rail, and light rail. And we also included BRT and ferry, because those really have some of the same station access issues that you would have along rail stations. In terms of the access modes that we covered in the project, we looked at the 4 major access modes, the high-capacity transit that people would think of: walking, bicycling, feeder bus or feeder transit, and then auto, whether by park and ride or by kiss and ride. And then we also included transit-oriented development as sort of a 5th access mode. It's not exactly an access mode, but because of a lot of the issues are similar in terms of how land is used around the station, and in terms of some of the trade-offs the agencies might face in terms of trading off TOD versus, say, expanded parking facilities, we incorporated TOD as sort of an access mode throughout the project. And then the next question, of course, for our research was, what's the problem that we're trying to address? And transit stations are rare and valuable assets, so of course we want to maximize the benefits that they're providing to communities. But saying maximize the benefits can mean a lot of different things, because when you're talking about transit stations, there are a lot of different stakeholders involved. From the transit agency that runs the service and may be most interested in increasing ridership and minimizing operating costs, to local jurisdictions that may be looking at economic development opportunities, or neighborhood associations that may be concerned about congestion caused by increased parking. There are a lot of different stakeholders and a lot of different goals for station access. Some of those goals are complementary and some of them aren't. And so what we're really looking at as part of this project is trying to figure out a way to evaluate the trade-offs and come up with solutions that make sense given the local station context for a given station. So a lot of what we did as part of the project was already covered in the first part of the webinar in terms of the planning process and what goes into that. So what I want to talk about specifically as in this part of the webinar is more on the data side. So 3 key components to this presentation. One is the station typology that we developed as part of the project. And then the second part will be focused on the station-specific data on transit access that we collected. And then finally, I want to spend a fair amount of time talking about the spreadsheet-based tool that we developed using the combination of the station typology and the data that we collected. So first, the purpose of providing the station typology was really we wanted to provide something that could provide a consistent planning framework for transit access. The graphic shown here is a conceptual graphic showing that, as densities decrease, auto access increases, and that's really good as a rule of thumb. But what the station typology hopefully can do is provide a bit more nuance to that so that there's more information that can be used for planning and more specific to individual stations. So the goal of the station typology was really to capture the important physical factors that affect station access. And the typology can be used both to categorize existing stations and then also as an aspirational typology. Is you can look not only what a station is today, but maybe what you want it to be in 20 or 30 years. And so we use the typology as a basis to organize the data throughout the guidebook and to help inform the access planning tool. So the station typology, there's a total of 18 station types that were developed, and it covers all the line haul nodes. So it is intended to be a comprehensive typology. And we recognize that few individual transit systems will have all 18 station types represented. And for a specific application, you may be able to collapse the 18 station types into 8 or 10, but we wanted to provide the full 18 to make it more comprehensive and more flexible for individual transit agency needs. And the graphics here just show two examples of station types, and you can see how the land use and transportation network differs between, say, a suburban freeway station and a suburban TOD. So the typology factors that we looked at, there are 8 key factors that we incorporated in while developing our typology. So the housing in this table shows both those 8 factors as well as one example for how those factors relate to one particular type, a suburban employment center, just as an example. So the 8 key factors are housing density, what the residential density is like surrounding the station, the scale of the buildings, what the surrounding land uses are like, what the land use mix is like, how far the station is from the central business district, what the supporting transit network is like, what the opportunities are for feeder transit service, how pedestrian and bicycle access works at the station, what the network is for pedestrians and bikes, what the connectivity is like, the availability of parking facilities, and then finally whether or not the station is what we categorize as an access or an egress station. So an access station would be one that is primarily used by people, say a residential neighborhood, people getting to the station to go to work, whereas an egress station might be a suburban employment center would be egress. Most people are getting off. They have their destination at the station, or like a stadium would be another example of an egress station. So the typology itself, it's summarized in the guidebook as a 2-page matrix, which can be printed out into an 11 by 17 table. And it's 18 station types by the 8 factors, and we provide example stations for each of the station types. So if you want to know what a real-world example of, say, a high-density urban neighborhood might be, we provide at least one example for each of the station types, as well as typical line haul modes that are associated with each of the types. So definitely don't want to go through this table in detail, but do want to say that this table provides a very important framework for a lot of the rest of the work that we did as part of the project. So the second part of what I wanted to talk about for this part of the webinar is once we had the station typology is the station access data that we collected as part of the project. And so we did this because we wanted to make sure that the typology that we developed was connected to real-world outcomes. And we wanted to make sure that it actually made sense and also provide a sort of base data from which we could develop a spreadsheet tool. And so the first input that we really needed to collect was what the station access characteristics were at different stations. What % of people are arriving at different stations by walking, by biking, by park and ride, and so on. And what we found through our case studies and talking to agencies was that most agencies don't actually have that data readily available at a station level. They may know it system-wide, but they don't know at Station A we have 14% walking, and Station B we have 18% walking. So what we did was we collected all of the station-specific access mode data that we could find. And we found it from 8 total transit agencies. We have 7 listed here, and I think New Jersey Transit also provided data and somehow didn't get into this table. In any case, so we have data from 8 different transit agencies across the country and representing a variety of different line haul modes. So I think we got pretty good representation. The data itself, from those agencies, we were able to collect station access mode data for over 450 stations around the country. So once we had that data, we manually matched it for each station to the typologies that we developed using whatever available data we had. And so we did this for 2 reasons. One was to confirm that our typology worked and that you could fit, almost all stations that we encountered readily fit into the typology, and we didn't have a whole set of stations out there that didn't fit any particular type. And then secondly, to provide a data set for further analysis. And so we captured a wide range of access characteristics in the data that we got. So Chapter 4 provides a lot of summary data tables to summarize what it was that we found. And I think probably the most important data table, or maybe the one that sums it up best, is this one shown here, which just shows the average access node percentages by the 18 different station types. So this is based on those 450 stations categorized by station type and looking at how access modes change depending on your station type. And we can see pretty clearly that there is a really wide range of access characteristics. So, for instance, walking access ranges from a low of 10% at suburban freeway stations to as high as over 80% at urban commercial stations. So we did see a wide range when we filtered the data through into our typologies. And then I do want to mention that for people that like data and want to see lots of data, Appendix D provides the full access data for all of 450 stations. So if you want to see tables of data, then it's all there in Appendix D, and it's arranged by station type. So if you wanted to know some example urban commercial stations around the country and what their access characteristics are, then you could find specific stations in Appendix D. So I think for the average reader, most of the summary information that you might want would be in Chapter 4 itself. All right, finally, I want to spend the rest of the time on this particular webinar talking about the spreadsheet-based access ridership tool that we developed, which is summarized in Chapter 5 of the guidebook, and is provided online as an Excel tool. And also in Appendix C, there are use instructions for the spreadsheet. So the purpose of the spreadsheet tool wanted to have a tool that could estimate station ridership for each access node and really be used in order to facilitate analysis of different access alternatives. So if an agency is maybe looking at investing in additional feeder transit service or expanded parking, or considering maybe developing a surface parking lot as TOD, having a tool that would allow them to assess the trade-offs associated with each of those alternatives was really what we were going for. And when we say assess the alternatives, there were three key outcomes of the spreadsheet that we wanted to have. So one, we wanted to estimate impacts on ridership. Two, wanted to be able to estimate impacts on operating costs. And then third, estimating impacts on transit agency revenues, both fares and parking revenues, as well as the revenues generated from selling land if applicable. So developing the spreadsheet tool really started in the literature review of the project and the stakeholder interviews that we conducted when we started the project in 2009. And what we found was that there are relatively few objective station access evaluation tools out there that are being currently used by agencies. Agencies may have rules of thumb that they use or elasticities or very, very simple metrics, but in general there was a lack of a comprehensive tool that could help agencies with these particular issues, which we did find most agencies were dealing with. One good example that we did find in the literature review was a spreadsheet-based tool developed by BART, and it was published as a TRV paper by Wilson and Minotti, I think in 2008 or 2007. And this was a tool used to assess trade-offs specifically between parking and TOD. And so we saw this and thought that it was a really good tool and something maybe we could expand as part of our project and make it a little bit more national in scope. And so in terms of our process for developing the tool, as I mentioned earlier, we've already had data collected for our 450 stations, and then we also had a station typology. So those were really the inputs that we used to develop the tool. Developed a draft structure, which was approved by the panel, and then the draft version of the tool was actually sent out to transit agencies across the country for testing, and so the feedback that we got from them was used to both enhance the functionality of the tool, what it was able to do, and the usability of the tool, making sure that it was in fact user-friendly and straightforward to apply. In terms of the types of factors that affect access decisions and that we wanted to incorporate into the tool. There are, of course, a lot of different things that affect how passengers get to the station. So for automobiles, parking and riding requires having available parking. If you're taking feeder transit, you need to have convenient service that's coordinated with the line haul. For biking and walking, you need to have good facilities leading you to the station. And then for biking, you need to make sure that you need to either have bicycle storage available at the station or allow bicycles on the transit vehicles themselves. So these are the types of decisions or the types of factors that affect decisions, and that we wanted to incorporate into the tool. For the variables that we would be able to use as inputs and sort of drive the modeling, we collected independent variables for everything that we could think of that might affect station access, but that also was nationally available. And so we got information on the parking availability and number of spaces, parking pricing, bicycle parking availability, number of connecting transit lines, as well as a range of demographic information and the walk score for each of those 450 stations. So we had a pretty robust data set of both access characteristics, which we could then match up to these independent variables. And of course, as I mentioned, our data for the stations came from across the country, and there are 450 stations. So we needed to have nationally available data sets. We couldn't go out into the field and collect data, so we had to rely on whatever we could find, basically from online sources. So the tool itself and the ridership forecasting that we developed, it works best where agencies have existing and projected boardings available that can be used to help calibrate the tool to local conditions. But you can apply it regardless of what data agencies already have available. And essentially, we developed a set of linear regression models that estimate ridership from each of the key access modes. So one model each for feeder transit, auto, pedestrian, and bicycle. And I want to point out it's of course not a replacement for regional travel demand modeling, but it is a way hopefully that agencies can identify key relationships between ridership and access and test different alternatives at a sketch planning level for a high-level look at how different access alternatives might work. So the next couple of slides here are the details of the regression results themselves, and I don't want to spend much time on that. Just to say we do have 4 different models, and the R-squareds for the auto, bike, and pedestrian we thought were pretty good, over 0.7, which shows that the models had a pretty good fit, really, given the type of data that we were looking at. For feeder transit, the R-squared is quite a bit lower. The model fit not nearly as well. And really we feel that was the result of not having good data available on the quality of service for feeder transit at individual stations. We were only able to collect the total number of connecting bus lines, but we didn't have information available on the frequency of those individual bus lines, exactly what the routes were, how reliable they were. That type of data just simply weren't available at a national scale. So the model findings, the regression results, the detailed regression results are available in the guidebook if you want to sift through the numbers. But the key findings are summarized in the next couple of slides. So first, we found that automobile access increases when you have more parking spaces. And that was really the primary determinant of the model, although, of course, we know that's not necessarily a causative relationship. There may be more parking because there's more parking demand and not vice versa. But we also did find in the modeling that higher levels of vehicle ownership resulted in more people choosing park and ride, and so that's consistent with our intuition. Bicycle access increased as population density around the station increased, so the more people within biking distance, the more people bike to the station. And also as vehicle ownership got lower, bicycling increased, which suggests that as we'd expect, as people don't have cars available, they seek other means of reaching stations. And then interestingly, we also found that more bicycle-friendly station areas measured by overall bicycling in the station area more bicycle-friendly stations had more bicycling to the station. So suggesting that if there is bicycle infrastructure in place and that people are comfortable biking in an area, that you're more likely to see higher bicycling to transit. Pedestrian access, similar results to bicycling, increases with higher population density, and as with bicycling, we saw that pedestrian friendliness in the station area was correlated with higher walking to the station. So it's not simply a matter of having people close to the station, but providing good pedestrian facilities, the modeling showed, also can help encourage people to walk to transit. Then finally, our feeder transit model showed that, of course, as you had more connecting bus lines, feeder transit increased. But not only that, that as parking became more constrained, feeder transit increased as well. So what that means is that if you had a parking facility that was near full, then you would expect more feeder transit than at a adjacent station where it was less full, all else being equal, which suggests that riders are willing to switch to other access modes, specifically to feeder transit, when parking becomes limited. All right, so I want to quickly go through a bit of overview of how to use the tool, and then close with a illustrative example of how the tool might be applied, just to give you a little bit more of a concrete example of what we're talking about here rather than just sort of the concepts. So the tool is available in an Excel spreadsheet, which we hope is a user-friendly Excel spreadsheet. And it's available online and on the CD that accompanies the TCRP 153 print version. Now the spreadsheet does use color-coded cells throughout, so that all input cells are a certain color, all the calculations are another color, and all the outputs are a different color. So that it should be fairly simple to understand what's going on in the spreadsheet. It's all formulas, no macros, so you can follow things around. And then Appendix C does provide step-by-step instructions on how to use it. I've got a couple of flowcharts here, one for each of the modes that describes in a little bit more detail what type of information goes into the spreadsheet and what type of outcomes you get. So starting with Park and Ride, the primary input into the model would be the number of parking spaces and the parking utilization. And depending on whether that shows that you have excess demand or excess capacity, you can then go through looking at different alternatives in terms of adding additional parking supply, pricing parking, looking at TOD to replace surface parking lot, and the outcomes for adding parking supply or changing parking prices really come out to sort of the cost per rider. So how many riders are you gaining or losing, and how much is it costing per rider? With the development scenarios, it really allows you to evaluate scenarios in terms of different parking replacement options. So if you, say, had a surface parking lot that you want to develop, but without subsidies, the market wouldn't support, say, replacing all the parking for commuters, going to a less than one-to-one parking replacement, what does that do in terms of ridership or revenue outcomes? For the feeder transit tool, it really starts with sort of the existing productivity of the feeder transit service in riders per vehicle hour. It looks at the cost per rider and allows the agency to look at, well, what type of ridership increase might be expected with increases in that amount of feeder transit service. And so, for instance, if an agency had a certain number or a certain amount of money available for access improvements, you could essentially use the tool to assess whether feeder transit service might be more or less cost effective than investing that same amount of money in increased parking supply. For the pedestrian and bicycle access tools, there was less data available to develop a robust tool. So they're relatively simple and work in a similar way, in that it basically ends up comparing the existing bicycle or pedestrian access at a station to what you might expect that pedestrian bicycle access to be given the station type and the surrounding land use. And if it's sort of below where you might expect it to be, then the tool tells you that, pedestrian or bicycle improvements are likely to be, pretty cost-effective and will work to increase pedestrian and bicycle access. So it's just kind of a screening. It helps as a screening tool to identify those stations that might be most in need of pedestrian or bicycle access improvements. Finally, on using the tool, I want to mention that there are, of course, default values provided for many of the data inputs. For instance, the annual operating cost per structured parking space. And those defaults allow anybody to go in and use the tool immediately. But we wanted to make sure that the defaults are one, clearly identified within the tool, so you know where it is that we're using a default. And the users are encouraged to modify default values for local context. So if an agency has better data available, the spreadsheet makes it very clear where to input agency-specific defaults and get a better fit within the tool. So I want to close quickly with an illustrative case study that maybe provide a more concrete example of how in practice an agency might be able to use the spreadsheet tool effectively. So here's an example station that, it's a light rail station in an urban neighborhood with about 300 free parking spaces that are pretty well, but not 100% utilized. Some parking and some transit. Other inputs to the tool that would be needed would be the station area demographics. So this is all information that would be available through census data, and so pretty straightforward to collect for the station area. And we used a half-mile buffer for developing the tool. And so you can see the demographics that would need to be collected to be input into the tool. So inputting the demographics and the station type into the tool, the first output that you will get is projected boardings by access mode. So this is what it shows you as the estimate, about 3,100 boardings per day, and a mix of different access modes. And so if the agency had had better data available, then this base output could certainly be calibrated to local data. But basically, this is sort of the starting point of what the tool provides. But what it's really intended to do is then allow planners to test different access improvements to understand which ones might be more or less cost-effective given the station characteristics. So in this case, maybe we're looking at charging for parking, $2 a day, adding some additional feeder transit service and improving schedule coordination from the existing service, and then improving the bicycle facilities in the station area. So if these are the types of things that we're looking at, what can the tool tell us about them? First, as you saw earlier, the parking supply exceeded the demand, which suggests that there's not a pent-up demand of additional riders that want to use the parking facility. So if you do parking pricing, some ridership will be lost. And so based on standard elasticities that we have in the tool, we'd estimate that at a net loss of 58 daily boardings. And that's because some riders will find another access mode. Data would show that about a third of riders, when priced out of parking, would then switch to another access mode, whereas 2/3 would simply stop taking the service altogether. At the same time, the feeder transit improvements in this case are estimated to add almost 400 additional daily riders. And then the tool will tell you that since the bicycle access mode share at that station is significantly less than sort of the regional bicycle activity, which suggests it ought to be, that the bicycle improvements are likely to be effective. And in addition to testing sort of transportation-focused improvements, we wanted to also make sure that the tool can be used to assess the impacts of different transit-oriented development scenarios. So here conceptually, maybe we might want to replace that 300-space surface lot with 270 housing units. That would be about what would happen if you put a 4-story apartment complex on that site. And for the sake of simplicity in this example, assumed no replacement parking. So those 300 spaces just go away entirely, but it's replaced with development. What happens then? Well, the tool would tell you that because of the parking loss, you've lost about 475 boardings per day. At the same time, the new development is generating about 300 boardings. And so you've got a net loss of about 175 boardings per day as a result of this development. Similarly, if you have land costs or rents, the tool can also provide outputs of what the cost and revenue impacts to the agency of this scenario would be. And of course, in the real world, it's going to be a little bit more complex than no replacement parking. And so you could input different options for replacement parking. So what if we replaced 200 out of the 300 spaces and did that in a surface in a parking garage? You know, what would the ridership impact and the cost impacts of that be? And so hopefully that provides a little bit more of a concrete example of how the tool might be used. I think there are a lot of different potential applications for it. In particular, I think what it allows is for multimodal access evaluation in terms of both ridership and cost. So you can compare the cost effectiveness of, say parking capacity increases with the cost effectiveness of other measures. And it does reflect factors that affect all four of the major access modes to transit. And as we talked about earlier, it's based on a pretty robust national data set of access characteristics at over 450 stations. And so, of course, this tool in and of itself can't make decisions, but I think it does provide value for decision making for station access planning. And so, for instance, it's already a slightly modified version of this tool has already been applied successfully by Sound Transit for a commuter rail access study on their Sounder system. I think it was called the Sounder Flexible Access Study, that wanted to identify cost-effective ways to increase ridership, partially through parking capacity increases, but looking beyond just increasing parking to figure out what else the agency might be able to do to increase ridership on its commuter rail. And this tool was applied there to estimate the cost effectiveness of specific projects in terms of cost per riders. So with that, I don't know if Kathryn, if you are available to provide the summary?
Yes, I managed to get back on. So just to summarize what we've done here today, the first session, the first webinar, covered the planning processes and the case studies and the design guidelines from the TCRP Report 153 that covered two of the major products that we had from this report, which were the guidebook and the case studies. And Jamie just finished up with this very valuable station planning tool, access planning tool. I looked at the station typologies that we had. I think together these two pieces of the webinar have given you a good overview of what's in the TCRP report. We're hopeful that you'll be able to just pick this up and be able to go directly to any of these resources to aid in your access planning activities. And one more time, again, there is the guidebook. A lot of this information, however, is in the appendices, A through E, that are included either on the CD-ROM in the printed report or available for download off the website, and that is also where you will find the actual tool. So with that, I would like to thank everybody for attending, and I think we're ready to turn it over for questions. So we'll turn it over to you, Judy.
Yes, hello. My question is on the example that was just given. What is replacing the 450 riders who were in that parking lot? Did I miss that?
So in that conceptual situation, all the park and ride spaces were gone. So if you lose 300 parking spaces, in that case, the tool was suggesting that you would lose about 475 riders. The development would, because you have transit range development, would provide about 300 riders a day, and so you would end up with a significant net loss in total ridership under that scenario. So nothing would be replacing those riders in that particular instance. Of course, there would be different, you could look at different options within the tool where you do replace the parking and have development and assess that in terms of ridership, although that would, of course, then cost more.
Are you just looking for a dramatic example of some sort, a very simple example?
Yes.
Okay. Because perhaps, you would also, how would you get 300 trips out of 270 units?
Well, it's daily trips, and so we looked at, each household would generate about 10 total trips a day, so you get a total of about 2,700 trip ends per day based on ITE rates, and about 10% of those might be captured by transit. At least that's what the tool would be suggesting.
Okay, thank you.
Hi, we have a question from chat. This question is about station typologies. The report expresses residential density as low, medium, and high. Do these have an assigned number of dwelling units per acre and number for floor area ratio for non-residential development?
We just decided not to give a specific number for that density, given how densities differ so dramatically from different regions across the country. So ultimately, we decided it'd be better to leave it as low, medium, or high, and leave it up to the judgment of the staff applying the typology to figure out how they fall into it. And that was sort of a judgment that the research team and the panel decided made the most sense. So I guess the short answer is no, there's nothing specific. It would be dependent on the region that you're applying it in.
Another question from chat. How can you download the Excel tool?
So from the TCRP Report 153 website, so if you were to Google TCRP Report 153, the tool is available as a link on that website. So it's an Excel file that you can download directly from the TCRP website.
Another question. In typology, why isn't LRT included as a mode for suburban freeway?
So the line haul modes listed are what we saw as the most typical. It doesn't mean that suburban freeway stations would never occur in light rail, and of course they do in some cases. So we saw them as most frequently happening in heavy rail lines along freeways, but there are some along light rail as well. So I guess those would be more typical line haul modes than all the line haul modes that it could possibly apply to.
Okay, another park and ride demand. Was size of CBD, number of employees considered in the modeling?
It was not. We wanted to include it. We could not find a consistent national data set that provided the same data for all the regions that we had data for on CBD employment or the size of the CBD. So one thing that we have in the model that sort of serves as a proxy for that is the heavy rail dummy variable, which heavy rail systems are more likely to occur in regions with large CBDs, and that dummy variable I think kind of serves as a proxy for CBD employment since we weren't able to find a consistent data set to incorporate it directly into the modeling.
The next chat question. Are there any plans to add more station data in the future to sharpen up the algorithm, especially for the feeder service part?
So the research itself is completed, so the research team wouldn't be doing that. The full data set is published as part of the report, so certainly anyone could take that and add to it, but as far as I know, there's no sort of program in place to create sort of a data clearinghouse that would allow it to be naturally expanded, although I think that would be ideal.
Here's another chat question. Does the tool identify parking turnover by station typology? For example, an urban commercial has a turnover of 3 riders per parking space versus a suburban freeway has a turnover of 1.2 riders per space.
We do have default values for parking turnover in the tool. We were not able to get station typology specific data on how those might change by station type. So if in fact, it is 3 riders per parking space for urban commercial and 1.2 for suburban freeway, that's not incorporated into the tool directly, but the default value is there. So if an agency had the data available to be able to say that one type is significantly different from another, that default value can easily be changed.
Another chat question. Is the proximity of parking an input into the tool? For instance, we would be interested to see the impacts of ridership if we replace adjacent parking with housing and move the park and ride a certain distance away from the station.
It's not incorporated into the tool itself. There is guidance in the guidebook on locating park and ride facilities and their proximity to the station in order to get the benefits from the park and ride. And I think the guidelines suggest that no parking space should be located more than a quarter mile from the station entrance, or the parking is at risk of being less used. So, and there's some more specifics in the guidebook about locating the parking facilities and how that ought to be done. So I would refer the questioner to the guidebook itself, and then depending on whether or not those criteria could be met, then the tool could be applied depending on the results of whether or not you could actually fit the parking and the development in within sort of that quarter-mile distance.
Another chat question. Could you please define heavy rail? I assume it means rapid transit and commuter rail.
Heavy rail would basically just be the rapid transit or the subway, the third rail. Commuter rail would be separate. So heavy rail would just be the subway system or the rapid transit.
Another text question. What is the assumed auto occupancy for park and rides?
I would have to go back and check. I think it's 1.1 or 1.2. It's the default value. I don't recall off the top of my head what it is in the tool itself.
And there are no more questions in the chat. Okay, then I think that we can conclude the webinar. I would like to thank everyone for participating in the webinar. Thank you, Kathryn and Jamie, for an informative presentation. Thank you very much.